All right, so we're in 9.2 now. We're talking about the sum and difference identities for the sine, cosine, and tangent function. The work that we do in this section to develop these identities is going to be what sort of opens up the path to section 9.3 and 9.4. In 9.3 and 9.4, we're going to discuss a number of different identities, and you can kind of trace all of them back to these ones. We're going to derive them essentially from these guys. So a sum or difference identities is an identity where we're working with an expression of one of these forms here: sine of alpha plus beta, or cosine of alpha plus beta, tangent of alpha plus beta, or swap out the plus for a minus. Basically, we're adding or subtracting two angles before taking a sine, cosine, or tangent of them. And what we want to do is come up with a way of expressing those without the sum or difference occurring on the inside there. So what we're going to do is do some work to derive these sum and difference identities, starting with the cosine function, and then we're going to work through some examples with how they're, how to use them, how they're useful for us. So let's start with the sum and difference identity for cosine. If you have cosine of a sum of two angles, alpha plus beta, then that's equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. So a product of the cosines of each angle minus the product of the sines of each angle is going to always be equal to cosine of the sum of those two angles, cosine of alpha plus beta. If we change this plus to a minus, so it's a difference of two angles, cosine of alpha minus beta, the identity looks almost identical to the sum identity, but the difference is that the minus here has been replaced by a plus. So let's see if we can derive these identities. So what we're looking at here is the unit circle, and because we're talking about two different angles, alpha and beta, I'm going to try and come up with a representation for each one of those in the unit circle. So for this case, this first red line, this radius of the unit circle, is going to determine this angle that I'm going to label beta right here between the positive x-axis and that radius. So that's beta in standard position there. Alpha is going to be the angle created by the positive x-axis and this this red radius right here, the one that's kind of furthest along in that rotation. Okay. Now, if I were to subtract these two angles, then I'd be starting at alpha and subtracting an angle beta. But notice when we subtract an angle, that's like rotating clockwise from whatever position we're at. And here angle beta would match this little angle right here. This is beta, this would also be beta. And so the angle from the positive x-axis to this red radius kind of in the middle between these two would be alpha minus beta. So you're seeing alpha minus beta way out here, but what that is that's this angle right here, okay? Now what we're going to do is employ the distance formula, something that you learn about in geometry and you also learn in intermediate algebra. And basically what the distance formula is a way of determining the distance between 2 points in the plane. So for example, if I have a point x1, y1, x2, y2, okay, it's just two arbitrary points in the coordinate plane. I could draw a straight line between those two and call the length of that line d. That length would represent the distance between those 2 points. Now in geometry and again in intermediate algebra, you derive this formula. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And because you derived this in a previous class, we're not going to go through the derivation of this distance formula here, but it really just boils down to an application of the Pythagorean theorem. So I'll just say that and move on. Now, here's what I want to do. I want to take a look at some of the points on the unit circle that are determined by these different angles. So first of all, notice that the angle alpha minus beta is the angle between the positive x-axis and the radius here kind of in the middle, leading to this point A right here. Okay? If I were to create this blue dashed line joining point A to point B, which is really the point 1, 0, it's on the positive x-axis here, then I've created a triangle. That triangle has this red radius, this blue dashed line, and this part of the positive x-axis as its edges. So hopefully you can see that triangle. Now if I took that entire triangle and just kind of rotated a bit until this red radius overlapped with this one, going to point P right here, then what I would have done is I would have moved that triangle through an angle of beta, right? Because we know that this angle here is beta. But this angle here is also beta. So what that would mean is that the radius here on the positive x-axis would rotate up to overlap with this red line. And the blue dashed line would then coincide with this blue dashed line. So basically that's created a second triangle right here. But because this second right triangle is just what we got from rotating this triangle and not stretching or compressing any of its sides, then those two triangles would be congruent. That means that corresponding side lengths would all be equal to each other. And where that matters is when we look at these blue dashed lines. So that argument would basically say that this blue dashed line has the same length as this blue dashed line. But both of those lengths can be interpreted as distances between points. So for example, this blue dashed line is the distance between the points P and Q, whereas this blue dashed line is the distance between the points A and B. So those two distances need to be equal to each other. And that's where we're going to end up coming up with this formula, or these identities. Here's how we're going to do that. So let's start by looking at the distance between points P and Q. I'm calling that dPQ for short. Okay, that's specifically the distance between those points. How do we compute that? Well, I would need to use my distance formula on the points P and Q. But what is the point P? Well, notice P is a point on the unit circle determined by the angle alpha. So that means the point P is equal to cosine of alpha, sine of alpha. Remember, we associate the cosine and the sine of a particular angle with the coordinates of a point on the unit circle. So those would be the literal coordinates of this point. What are the coordinates of point Q? Well, Q is a point on the unit circle determined by the angle beta. So its angle, or its coordinates would be cosine of beta, sine of beta. All right? So what we're doing is we're using the distance formula on these 2 points with those coordinates. x2 minus x1 is going to look like cosine of alpha minus cosine of beta. So that's what we're seeing here, cosine of alpha minus cosine of beta. And then we're squaring that because that's what the distance formula calls for. Similarly, the y2 minus y1 in this case is going to look like sine of alpha minus sine of beta, and we're squaring that. And from here, it boils down to some simplification and using our Pythagorean identity in that process. So if I were to square this first difference here, cosine of alpha minus cosine of beta squared, I would get these 3 terms. Cosine squared of alpha minus 2 cosine of alpha cosine of beta plus cosine squared of beta. We're squaring that the same way you would square, something like a plus b quantity squared in algebra. Same idea. Similarly, this guy here, sine of alpha minus sine of beta, would expand out to this. It looks very similar to these 3 terms, but with sines instead of cosines. Okay, and now what we're going to do is try and simplify this as much as possible. So here's what I notice. We have a cosine of alpha plus a cosine squared of alpha plus a sine squared of alpha. And if I were to take those 2 terms and group them up, my Pythagorean identity would tell me that this is equal to 1. So I can simplify that a lot just by combining these and making them equal to 1. Same thing with cosine squared of beta and sine squared of beta. If I group those up and add them by my Pythagorean identity, that equals 1 as well. That leaves me with these 2 other terms, negative 2 cosine alpha cosine beta, negative 2 sine alpha sine beta. And I'm just kind of moving those over to the right here. So both of these, based on what we just talked about, are equal to 1. And so I say 1 plus 1 here. And then that would just equal 2. And so all this, even though it doesn't look terribly simplified, it does look much simpler than what we started with. It's equal to the square root of 2 minus 2 cosine of alpha cosine of beta minus 2 sine of alpha sine of beta. Again, that all came from the distance formula and then just simplifying what we got in that process. What we're going to do is leave that alone for a second because, again, that's the distance between points P and Q. Now what we need to do is find the distance between points A and B because that should be equal to this distance. So we'll come back to this and set what we get in the next step equal to that. In order to use the distance formula on points A and B, we need coordinates for those points. What is the coordinates of point B? Well, I mentioned a little while ago, because it's on the positive x-axis and it's on the unit circle, its coordinates have to be the point 1, 0. What are the coordinates of point A? Well, A is the point on the unit circle determined by the angle alpha minus beta. So the coordinates there are going to be cosine of alpha minus beta, sine of alpha minus beta. Okay? So these 2 points are the ones that we're using our distance formula on now. And that's happening right here. So again, notice x2 minus x1 is going to look like cosine of alpha minus beta minus 1 quantity squared. And then similar for the sine. Notice the y2 in this case is a 0. So I'm subtracting 0 instead of 1 here. If we square these out, this first guy right here, cosine of alpha minus beta minus 1 quantity squared, is going to look like this. Cosine squared of alpha minus beta minus 2 cosine of alpha minus beta plus 1. And then because this minus 0 is here, we can just kind of ditch it, and really all that's left is sine squared of alpha minus beta. Once again, we have 2 terms that can be combined using the Pythagorean identity, cosine squared of an angle plus sine squared of the same angle, alpha minus beta. So here we group those up and then use the Pythagorean identity to say that these 2 add up to just the number 1. 1 plus 1 is equal to 2. And now we have 2 expressions, one for the distance between points P and Q, one for the distance between points A and B, and based on the argument we started with, those need to be equal to each other because of how they're arranged in this unit circle diagram up above. So finally we set those equal to each other. And squaring both sides will get rid of the square roots. So we have 2 minus 2 cosine of alpha cosine of beta minus 2 sine of alpha sine of beta equals 2 minus 2 cosine of alpha minus beta. If I subtract a 2 from both sides, I can get rid of those. And then if I were to factor a negative 2 out of both sides, or even think of it this way, if I just divided both sides of the terms that are left by negative 2, this would become cosine of alpha cosine of beta plus, because I divided by a negative, plus sine of alpha sine of beta equals cosine of alpha minus beta, this. And that is your difference identity for the cosine function. Okay, you can go through very similar steps to establish the sum formula, which again looks very similar to the difference formula or the difference identity for cosine, just with a minus where we had a plus originally. Okay, so that's a long derivation. There's a lot to kind of go through there. Let's get into something a little bit more concrete, an example. What we're asked to do here is evaluate cosine of 2 pi over 3 plus pi over 4. And there's technically 2 ways of going about this. One way is to add these 2 numbers together and then try to take the cosine of that single number that you get from the sum. However, it's possible that even though both of these numbers are on the unit circle, on the unit circle that we have memorized, the sum may be an angle that we don't recognize from the unit circle. And so if that were the case, this approach is not going to be very helpful because we won't have an answer readily available. So let's try using the sum identity to see if that's any easier. So this would be equal to, according to the sum identity on the previous page, the product of the cosines of alpha and beta. This is like alpha, this is like beta. Cosine of 2 pi over 3 times cosine of pi over 4. For the sum identity for cosine, if I have a plus here, I'll end up with a minus here. I get the opposite sign of whatever this operation was. And then I have the product of the sines of these 2 angles, 2 pi over 3, sine of pi over 4. Sorry, that's a little bit sloppy. What is cosine of 2 pi over 3? Well, that's in the second quadrant. Cosine's negative there. Cosine of 2 pi over 3 would be negative 1/2. What is cosine of pi over 4? Root 2 over 2. Minus, what is sine of 2 pi over 3? Sine is positive in the second quadrant, and that's root 3 over 2 times, once again, sine of pi over 4, which is root 2 over 2. If we multiply these together and then combine all of the results into a single fraction, a rational number, I get negative root 2 minus root 3 times root 2 is root 6, so I get minus root 6 all over the product of my denominators, which would be 4. So that would be my answer. Okay, and that alone tells me that I probably wouldn't have gotten a good answer by adding these two things first and then trying to take the cosine of the result, because this doesn't look like something I would have gotten from the parts of the unit circle I've memorized. Okay, let's take a look at another example. I want to evaluate the cosine of 15 degrees. We're going to use degrees just to kind of mix things up a little bit here. 15 degrees is not a number that I recognize from the unit circle. Now, yes, I could plug this into a calculator, but what's a calculator going to do? It's going to approximate a result. It's going to round it. And I want to be able to find this exactly. Or in other words, I want to be able to get an answer in radical form. The trick to doing this is to try and take the number 15 degrees and represent it as either a sum or a difference of two familiar angles from the unit circle. So notice, cosine of 15 degrees is equal to cosine of 45 degrees minus 30 degrees. Right? 45 minus 30 is 15. But the purpose of putting it in this form is that 45 and 30 are both degree measures that I recognize from the parts of the unit circle that I've memorized. So this is equal to cosine of 45 degrees, cosine of 30 degrees. Here's where I'm using my difference identity for cosine. If I have a minus here, I'll have a plus here. Sine of 45 degrees, sine of 30 degrees. And now I just resort to my knowledge of the unit circle. What is cosine of 45 degrees? Root 2 over 2. What's cosine of 30 degrees? Root 3 over 2 plus sine of 45 degrees, which is root 2 over 2. Sine of 30 degrees, that's 1/2. This is equal to root 6 plus root 2 over 4. Similar looking answer as the previous one, but not the same number. Okay? In fact, these are opposites of each other. So that's a couple of examples using the cosine identity that we just derived. But we still need to do the same thing for the sine and tangent functions. Both of those have difference and sum identities that we want. And fortunately, knowing the cosine, the sum and difference identities for cosine, allows us to derive the sum and difference identities for sine without having to go through that entire unit circle distance formula derivation that we did on the first page. It's much faster now. So here's how we do this. I would like to come up with an identity for sine of alpha plus beta. Now, rather than, again, return to that unit circle idea, remember we have a cofunction identity that says sine of x is equal to cosine of pi over 2 minus x for any angle x. This is one of the 6 cofunction identities that we talked about way back in chapter 7. Well, in this case, angle x looks a little bit more complicated. It looks like alpha plus beta. So in this case, the cofunction identity is going to look like cosine of pi over 2 here minus that angle, alpha plus beta. But you have to put that angle in parentheses if you're subtracting the whole thing. Otherwise, you're only subtracting the alpha. So if I were to distribute the minus to get minus alpha and minus beta and then regroup the first two terms, I end up with cosine of pi over 2 minus alpha minus beta. Notice the parentheses around those first two terms. What is this, though? This is the cosine of a difference between two angles. One of those angles looks a little more complicated than the other, but it's still just two angles. So now applying my difference identity for the cosine function, I would get cosine of this angle times cosine of that angle. Cosine of pi over 2 minus alpha, cosine of beta. A minus here means we want a plus here. Sine of each angle, I'm taking the product of those. Sine of pi over 2 minus alpha, sine of beta. Okay, finally, cosine of pi over 2 minus alpha, according to my cofunction identity, is the same thing as just sine of alpha, sine of alpha. Similarly, for one of our other cofunction identities would say that sine of pi over 2 minus alpha is the same thing as cosine of alpha. So these two factors can be simplified even further. And that gives us a sum identity for sine. Sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha sine of beta. Nice. So we'll use that in an example in a little bit, but let's also, while we're at it, derive a difference identity for sine. If I replace this plus with a minus, then the difference between these two things is that I have, sine of alpha minus beta instead of sine of alpha plus beta. But rather than go through even, a similar derivation to this one, it's always possible to think of subtraction as addition. And in fact, it's very useful to do that a lot of the time. Rather than think of this as alpha minus beta, let's choose to think of it as alpha plus negative beta. And the purpose of doing that is because I just derived a sum identity for sine, and now I'm looking at a sum of two angles here. So I can go straight to my sum identity for the sine function and represent this as sine of my first angle times cosine of my second angle, sine of alpha times cosine of negative beta, plus cosine of the first angle times sine of the second angle, cosine of alpha times sine of negative beta. In this last step, I can simplify these two factors by remembering my even and odd identities. Cosine of negative beta is the same thing as cosine of beta, because cosine is an even function. Remember, it kind of eats up those negatives. Sine of negative beta is the same thing as negative sine of beta, because sine is an odd function. Negatives can be brought out. But this sine is part of a larger term here, so let me bring the negative all the way out to this plus, changing it to a minus. And there we have our difference identity for sine. Comparing that to our sum identity, looks almost identical, except I have a plus here where I have a minus here. Okay, so here are those sum and difference identities again, just to restate them. And notice kind of the difference between your sine and your cosine. When we talk about a cosine here, cosine of alpha plus beta, then the plus here becomes a minus here. So we use the opposite sign in the case of cosine. If I'm using a sine identity, sum identity for sine or a difference identity for sine, the operations match. A plus here means I have a plus here. A minus here means I have a minus here. What's also different for a cosine, sum identity for cosine, the product here is going to be a product of cosines, and the product here will be a product of sines. In other words, we're multiplying the same type of function in each term, cosine times cosine, sine times sine. In a sine sum and difference identity, we're mixing the types. Sine of one angle times cosine of the other, and then cosine of the first angle times sine of the second. Similar here, okay? I'm only saying all that to help you with some of the memorization, because ultimately you do want to have these things memorized. All right, so here's another example, similar to what we did in the cosine example, but we just used the sine identities now. So sine of 135 minus 210 degrees. Now I could do the subtraction directly and then try and take the sine after that, but let's practice using our difference identity for the sine function, since we do have a difference here. This would equal sine of my first angle, 135 degrees, times cosine of my second angle, 210 degrees. The sign here, the operation of minus, will match what I'm using here, so I get minus. Then I take cosine of the first angle, 135 degrees, times sine of the second angle, 210 degrees. Okay? And now we just resort to our knowledge of the unit circle, since both of these angles are on the parts of the unit circle that we have memorized. What is sine of 135 degrees? Well, that's root 2 over 2. What's cosine of 210 degrees? That's negative root 3 over 2. Minus cosine of 135 degrees, which is negative root 2 over 2. Times sine of 210 degrees, which is negative 1/2. Okay, so here these are going to multiply to negative root 6 over 4, and I'll put the 4 at the end. Here I have a minus, minus, minus. So it's like a product of three negatives, which will be negative root 2 over 4. There we go. Okay, not too bad. Here is a seemingly much more involved example. Not seemingly, it actually is more involved. I really like problems like this. Keep that in mind when it comes test time for this chapter. So this may look like a gigantic mess, but if you think about it, we back in chapter 8 learned that inverse functions, inverse cosine, inverse sine, we want to think of those as angles because that's what they represent. In other words, the answer to this would be the angle or an angle that I could take a cosine of to get 1/3, specifically an angle between 0 and pi. Similarly here, an angle between negative pi over 2 and positive pi over 2, whose sine is equal to root 3 over 2. Okay, so we have a couple of approaches here. First of all, this I don't know the inverse cosine of 1/3 off the top of my head, since 1/3 is not something that naturally pops out of the unit circle that I have memorized. But I do know what the inverse sine of root 3 over 2 is, because that one does come from the unit circle. So I'm going to start by rewriting this in a slightly simpler form. Inverse cosine of 1/3, nothing I can do with that quite yet. But what is the inverse sine of root 3 over 2? Well, we know that one already. That's pi over 3. Okay? So that's going to help this be simplified a little bit. But the next thing I want to do is recognize that I have a sine of a sum of two angles. And that's something that I can use my sum identity on. So what would that look like? Sine of the first angle, sine of cosine inverse of 1/3, times cosine of the other angle, cosine of pi over 3. Because I have a plus here, I'll have a plus here. Cosine of the first angle, cosine inverse of 1/3, times sine of the second angle, pi over 3. And now I have four things that I need to find. I need to evaluate this term. I need cosine of pi over 3. I need cosine of cosine inverse of 1/3, and I need sine of pi over 3. 3 out of these 4 things I can do right away. Cosine of pi over 3 and sine of pi over 3, I can find those easily because I know my unit circle. This one is just going to equal 1/3 because this cosine on the outside will cancel with this inverse cosine on the inside and leave me with just 1/3. This is the trickier one to evaluate, but we've done problems like this in 8.3. How do you find the sine of the inverse cosine of 1/3? Well, remember, I'll do this down here. If I set cosine inverse of 1/3 equal to theta, again, we're thinking of that as an angle, then that implies that theta is equal to the cosine, or sorry, let's go like this. That implies that cosine of theta is equal to 1/3. And this is where we break things down into a right triangle. So I'll come back up there in a second. Create your right triangle. Label your sides. If this is theta and cosine is adjacent over hypotenuse, then I would have a 1 here and a 3 here. Using the Pythagorean theorem, which you can do this part, you should be able to determine that this side is equal to 2 root 2. Okay, so with that said, what is it that we're actually looking for? Sine of the inverse cosine of 1/3, or sine of theta. What would the sine of theta be here? Opposite over hypotenuse, 2 root 2 over 3. So that gives me the last piece of this puzzle up here, and I'm going to put in all the values that I know. What we just found is that sine of the inverse cosine of 1/3 is equal to 2 root 2 over 3. Cosine of pi over 3 from my unit circle is equal to 1/2. Cosine of the inverse cosine of 1/3, remember they cancel. This should be a plus. And that leaves me with just the 1/3. Sine of pi over 3 is equal to root 3 over 2. Okay, the product of my numerators here is just 2 root 2. Product of my numerators here is root 3, and both denominators multiply to 6, so that common denominator allows me to add them into one fraction. And there's your answer. Okay, that's all the time we have for this video. We'll keep going in the next.